Hello everyone, nice to have you back in our discussion of Kalman filters in MATLAB and in R. But before we move into move into the application part, as we know this is a series of discussion in line with the theory video we uploaded on Kalman filters. There is a few MATLAB functions that I want to focus on that I am hoping is available for R2. First is to know a function called vec. What vec does is whenever you give it a matrix, it precisely indexes it, so it makes it one series so that you can understand or you can play with the positions of each element. So it stocks a matrix into one column with Gauss vec. So that is a vec function. You vectorize a matrix, then you can play with the elements, you can actually matrix it back. Another one is very important, Recursive. We have used Recursive equation in function in different chapters in autoregressive discussion. In vector autoregressive discussion is nothing, it just creates a series basing on autoregressive equation, which is 5yt minus 1xt. So it creates a recursive series, that's all. It solves one equation again and again and again, updating the estimation results. So for example, there in the Recursive function you have x, y naught and a. A is the lag or the lag parameters, or autoregressive parameter. Y naught is the starting value, and one important factor is the lag parameter and starting value both are probably vectors, or both gives you the same dimension, both are p by k matrix, right? And x is the exogenous variable for which you are creating the series, and that is an n by k. The dimension for x is a bit different, which is n by k. So that's all. So for 1 to n, given the lags and given initial value, you create a series, and that is the Recursive series. And I'm not gonna go into the detail. So Recursive simply depending on initial value and autoregressive parameter, it creates a recursive series which follows an autoregressive system. That's all. System of equation, that's all. Or yeah, so if you, for example, 2a plus 5, now a equals 1, then 2a plus 5 you have 7, right? Now you can put the 7 in or you can solve for a using 2a plus 5. The result you find that you jack in, or 7 that you jack in to a. So 2 7 plus 5 is the next step. 2 multiplied to 7 plus 5 is the next step. So it goes on like that. So Recursive, a recursive series that is created with time series properties, or a dynamic series is created based on our given initial value and autoregressive parameter. Then another function, that is seca. Now it's basically seca gives a sequential series that has a starting value that goes in steps, right? And number of values created. So it gives you a series where it's a step-by-step, it's a stepwise series created depending on number of values. So if you start with 1, and if your step is 2, and if your number of values is 20, seca will give you 10 a series with 10 values. That's all. That's the simple. It simply creates a stepwise series. Now principal component analysis is a inherent function to estimate latent vector models, where the coefficient of the principal component analysis requires, the coefficient itself is lambda, which is our latent factor or Kalman factor, So if you run this function, it will give you the latent factor lambda. And what do you include? You basically include, first of all, this system automatically removes nuns. So any non element is automatically removed. Then you include the s, the value of s is included here, the score. Then in the next function, in place of name, you include principal component analysis variances. Okay, and you also mention what type of algorithm are you using. You mention what type of decomposition are you using. So t-squared is to modeling t-square estimation, explained is total variance is explained, and mean. So these things are also included in the function. So basically the function gives you lambda, whereas you include s, you input the variances, the steps, the things that we measure in steps, plus you can input t-square, or you can input, basically you can input what type of equation you want from the system. Like these are the types of equation you want. Do you want row by row estimation, or do you want eigenvalue based estimation, do you want algorithm based estimation? So that's all, what type of analysis you want. And the values can be like the values for variances. How do you want the total variance to be estimated? With singular value decomposition, sigma square v, eigenvalue pairwise, regular sigma square. So this is what it is. So these are a few equation functions that we might be using. So let's get back to our problems. First problem is, to begin with, recursions of the Kalman filter. Right now, in this equation, in this problem, you have two files, lfac uni and lfac smooth. But before that, I'm just gonna take 1 second here. Yeah, consider the univariate latent factor model with n is equal to 1 variable and k is equal to 1 factor. You know the state equation, measurement equation, you know the state equation. We are given the initial parameters. The sample size is t is equal to 5 with values are y. So we need to, at time t1 we need to estimate these equations. At time t2 you want to estimate the prediction equations, and that we want to do for up to 4. Then we want to estimate j or smoothed factor, and we want to repeat this process. So it should be easy and interesting. So lfac uni, lfac smooth. So lfac uni and is the univariate, and lfac smooth is the smoothed factor one. So we'll start with lfac uni. Let's move it here. Next, lfac smooth. And here lfac uni is open. So here we'll need a lot of obviously we'll need quite a few local functions before we move on. And univariate Kalman filter, first of all, I think this problem requires simulated sample or given value, I'm not sure. Anyway, I'm just preparing for the simulation, where removing in R, I'm removing the previous stuff. All equals true, E is equal ls all true, list equals ls or list all true, rm remove object, graphics of then set seed, 1 2 3 4 5 kind master and twister. Here random stream set global stream, obviously that will be there somewhere, so it's there, empty19937. Fine. So the function that I want to create is the whole univariate Kalman filter algorithm function. And what do we have? First we want to unpack the parameters. So lambda, sigma, the unknown parameters, lambda, sigma, what are our unknown parameters, lambda, phi, sigma, and sigma square v. So b1, sigma is v2 square, phi v3, sigma square v is v4 square. So we want that to represent v1 v2 square. So we want to represent yt, st, pt, mt, vt, ut, Kalman, blah blah blah. Lot of strings are there. So basically we want to create that table that we have discussed in our theory. So let's allocate arrays first. T equals length of y and log L, because log likelihood function will create up until 5, t equals 5, so 0 t rows, 1 column, so replicate 0 t times. So initialize, first initializing, and what do you have? S naught, so we have S naught equals 0 as we know, and P naught equals sigma square divided by 1 minus phi, sigma square divided by 1 minus phi square. So sigma square divided by, I think sigma square value is given to us in the question. Is it in the question? I'll just have a look. Sigma is 0.5, sigma square v 1, so 1 divided by 1 minus phi square. Beautiful. Then comes mu equals lambda into S naught, which is lambda st. Then mu1, then v1 equals what equals lambda square p naught plus sigma, lambda square p naught plus sigma square v. So lambda square means we can kind of like decompose it, lambda into pt into lambda, lambda into p naught into lambda plus sigma, lambda into p naught plus lambda into sigma. Fine, v is created. So we are doing initializing with Harvey and Hamilton. Then mu then ut is y1 minus mu naught mu1t, sorry, y1 minus mu1 0, so not 0, so s1 0, p1 0, m1 0, vt. So we have updated them. S1 0 equals s0 0, so p naught, so mu1 0, v1 0, u1 0 is equal to y1 0 minus mu1 0, right? Then log likelihood function is half log twice pi minus half log determinant of v, as we know. Then half we remember y1 minus mu1 0 transpose multiplied to omega inverse, then multiplied to y1 minus m1 0 transpose. So simply u square omega inverse is vt divided by vt, or the conditional vt was the variance, right? Which is the variance. pt is actually p10. P10 is the variance. Then we have it. Then Kalman gain equation is simply lambda, well, as you know, lambda p10 divided by v10, so lambda into vt, right? So this is the variance, conditional variance. U square omega is the variance, and then comes st, then s1. Then we are updating. So s1 equals so we had now we better our prediction, which is s11 is equal to s10 plus the Kalman gain equation multiplied to the y1 minus mu10, which was the y1 minus mu10, which is here ut. Okay, fine. Y1 minus mu10, the prediction error. And we know p10 equals and we know p11, which is a better forecast, is p10 minus the Kalman gain equation multiplied to which was simply the Kalman gain equation was what? Let's have a look. Why did I forget that? The Kalman gain equation, I'm just gonna, okay, so lambda squared, that was okay, p10 is minus lambda square. So okay, here it is lambda square, the numerator gets squared, remember, of the Kalman gain equation. So lambda square p square 10 divided by the v10. So lambda square p10 means, in general Kalman gain equation we have lambda 1 p10. So you take lambda 1 p10 divided by v10 out, you have the Kalman gain equation. So what you are left with? You are left with another lambda and another p10. So that's it, Kalman gain, lambda and p10. That's all, very simple. So this is initialization. Then display the initialization, which is table of results. So create, combine, iteration, yt, all these, and results table should have matrix well, the number of rows t, number of columns is equal to length of the c names. Dimension name is list of replicate all rows up until t, I mean all the columns here up until t, and c names based on that. And a quite difficult code here just to create a table. I'm having a matrix with one dimension name, and I have never used this before. Use this extension of the function. This will list the replication of the c names t times, and all table results, first row, I mean for all columns you have 1, y1, stmt, all this, log of l1. Okay, it's very much simpler, much simpler in MATLAB. If you're comparing this with MATLAB, it's much simpler. Filter initialization, y1, the first one, so c1, then c combine first ones, then y1. Ones will have the numbers, just the IDs, y1, then sp, s1, p1, then the forecast error, actually mu1, variance v1, then u is the prediction error, then Kalman, then log likelihood function. Okay, so now let's do the loop over the observations, because we initialized with just the first step, then the next step. So now for 2 to up until t observations, we do it again. And so the prediction is s1 is equal to, as we know, s1 is equal to phi 1, s1 is equal to phi s0, then p1 is equal to p1 is equal to phi square p0 plus vt, and phi square is phi into phi. Then observation prediction, you're going to use s10 and p10 for mu10 is equal to simply lambda s10, and v10 is simply lambda square p10. So lambda square p10 plus sigma square v. Now we are going to use these conditional mean and conditional variance from the previous variance and the mean, estimated from the previous variance and the mean. This conditional mean and variance is used to find the prediction error, which is y1 minus mu10. So for all yi, residual is created for all yi and empty, all empty. So very simple. Then comes observation stage is ready, where you have to consider mean and variance. Then we do log likelihood function. Indeed, it's important to do the log likelihood function. So half log twice pi minus half log determinant of v minus half multiplied to u square divided by the omega or conditional variance. And then we update is using the log likelihood function will be used somewhere, I'm not sure. Anyway, no, it's not used. We're just creating a series of the log likelihood function, that's all. It's not necessary to do that. So update we need to update. So S11 mine equals S10 plus kappa multiplied to y1 minus mu1 0, or kappa is Kalman gain, which is lambda p10 divided by v10. Then S10 plus kappa by v1 minus mu10, and then p10 equals to p11 equals p10 minus sigma lambda square p square 10 divided by v10. So basically you have the Kalman multiplied to lambda and kappa. That's all, very simple. So lambda and p10. So that is updated. Then let's display the results. Iteration will happen cat n print t table results. Okay, so this is the table results for I rows, all these. So print this table results. Beautiful, simple and usable table results. Automatically create the tables. Here is also display iteration, how many iterations are happening, show this additional, then show all these y I for because as y goes forward everything else goes forward, because it's a loop. And here I have provided I, so I'm putting I here. For the rest of them I have not provided anything. This is something I will replace here, and the rest will be automatically calculated based on this. Everything else have y inside of them. So basically just this thing we need to remember, we just allow y to change and rest will change. And display. So beautiful, simple but beautiful system. Then I think what we call for is uni, and the next question is LFAC smooth factor. And for smooth factor we know smoothing equations already, so just have a quick look in smooth function. Smoothing is backward propagation, right? And for this we have done everything just before, as before we unpacked. I'm not sure why predicted factor estimates updated, all these are zeros are created. I'm not sure if this even necessary. Allocate arrays, so many. Okay, this should have been done even before, because we didn't do allocate the arrays for all the parameters that we estimated, because that was only 5 step. If we do for larger steps we should allocate arrays, right? So rest is same up until S1 and S11 and P11, everything else remains same, nothing changes in initialization. So we are saying that sub1 is S11 and pop1 is P11, which is basically S11 and P, which is basically looking back to our smooth extraction equation, right? So let's start with that. Okay, looping is done. Again we are gonna use S11 and P11 now, the backward recursion. So SSM t is equal to S11 up until t. So what was the equation first? So we're gonna do backward propagation, very simple. We're gonna do reverse, you see, not replicate but reverse the sequence. Again reverse the sequence up until t minus 1 period. So we are saying SSM, which is smooth factor, will have our estimated result that we did for S11 and P11. The prediction, we are going to use that for t periods. So I equals t minus 1 till 1. Reverse it, not replicate it forward. The sequence will be reversed with this particular command. and it will reduce by -1. So what was J? J was P11 phi transpose divided by P21 phi transpose divided by P21. So P11 phi divided by PPR I plus 1. What is PPR? P21, which is to be estimated, I guess. PPR I plus 1. Have we estimated PPR somewhere? I don't think so. Okay, I'm sorry for singing. No, predicted factor covariance. No, we have not, because this is a function. Okay, this is a function and we want our system to estimate this automatically, because what is the difference with this earlier function? I missed something in earlier program. I'm really sorry. I was the log likelihood function comes into play. I completely missed it. So you see, in the earlier program, all these were defined in the functions, and I thought that is it. No, that was just the local function. Then we simulate the data given the earlier previous equation, where residual is based on we don't need to simulate data, we can use our own data. Anyway, residual is based on random numbers. V is random number, both of the residuals. Using that, we estimate F, because Y is lambda phi. What is Y? Y was lambda into S plus mu. So we are actually estimating S here instead of S, because we have used S so many times. We are using F. Recursive function comes into play. What is recursive function? Recursive series, as I told you in the beginning, that we're gonna create a recursive series which is coming from the state equation. What was the state equation? So this is lambda S, right? So S is equal to phi st minus 1, right? So that was simple, as simple as that. So here V is the recursive series that will be generated, that we want to estimate here. I mean, V has random numbers. I'm sorry, we want to estimate phi. V is exogenous variable. The S is equal to S phi minus 1 plus V. V is exogenous variable. We are using V as exogenous variable. We are using with we are initializing with 0, and phi is something that we want to we are using phi as well. So as exogenous, we are using V. S is equal to S phi minus 1. S is equal to st minus 1 phi st. So Y equals phi yt minus 1. S is equal to phi st minus 1. So phi is given, V is given. V is exogenous, phi is, and 0 is initialization, Y not. And we have Y estimated from recursive function, right? Now this whole thing was not necessary. We are just estimating a latent factor model. This is a new thing we learned. Simulate a series based on latent factor equation. Okay, and Kalman filter is simply calling the function, okay, that will solve your lambda, sigma, phi. That will give you all the results for lambda, sigma, phi, and sigma e. So you are estimating. So these are the thing. Kalman filter finally gives you all your theta parameters, unknown parameters. It gives you the value for lambda, it gives you the value for variance, it gives you the values for autoregressive parameter and sigma square v. Those are your unknown parameters, right? So that's all. You call the function Kalman filter here. Oh, so here in R we also have recursive function, where u and v both are created randomly. We use that, we transpose it to column bind 0, column bind phi. Okay, very important. Inside the recursive function, all the elements are used to call in columns. So column bind, column bind, column bind. I repeat, column bind, column bind, column bind within all elements in recursive function. And we estimate, we simulate Y. This is simulation by estimation. And then we simply call the log likelihood function that automatically generates your result. Simply call the log likelihood function, that's all. So display results, not necessary here. Univariate. So this function is called theta naught. Kalman filter, you have initial values. So we simulated the data, we initialized our data, and we called for the function theta naught, and it gives us these elements. I think those elements are basically automatically jacked into the system later on. Passing into these elements that are unknown to us automatically from this log likelihood step forward automatically allows us to, you know, find all these values, and basically this is what you're looking for, latent factor lambda based on the prediction. Beautiful, right? So smooth. I'm sorry, so smooth. I totally forgot about that. So smooth. So top one is latent factor smoothing, SSM. And what do we have? So what was I talking about? I'm sorry. So as we're talking about P11 and everything, so I T minus 1 to 1, J is equal to, you know, P11 phi transpose divided by P2 1. P2 is I plus 1. So PPR is something that has not been estimated, it will be estimated later. Then SSM, the smoothing factor is SSM is S1 for all T, for the entire T, S1 for the entire T, then S11 plus J multiplied to S2 for entire sample, so SSM I plus 1, S2 for the all for entire sample minus S21, so S2 and S21. Here you see this is S2, but this is for the entire sample, this is not for the entire sample, this is based on S11 multiplied to G. A bit complicated, but sometimes you have to memorize a few things. This is coming from our prediction, right? And this is will be predicted later, SSM and PPR. And then this equation LFAC, this function will have the smooth factor stored. That's all. Now let's go back. Okay, so we have defined the algorithm. Now the system will use this algorithm to give you unknown parameters, right? So simulate again, just like that, Recursive, everything remains same. Then call the function. If you now plot y and LFAC, you'll see a smoothened plot, much smoother plot. So this is all that matters. The log likelihood function parameters that are estimated, you know, this is all that matters. LFAC. So log likelihood function, using that log likelihood function, univariate LFAC, which will give you y, beta parameter y estimate. Input will be b and y, initialized with b and y, that will be smoothened. This will give you lambda, sigma, variance, and sigma square b. So let's go back to the question. So we are always trying to compute the following equation, results with those estimates of conditional factor means, and we obtained previously. Okay, all right, great. Then comes the next question, which is, so did we have any difficulty? One thing to remember, inside we need to create our, if we have a simulated equation, not an observed y, we can use an observed y or given y. We can use input that is given to us. Yes, we can use an input that is given to us. If not, we might want to estimate y based on, you know, simulation, based on simulation initialized with something. If not, we can simply use y, that's all. and our parameter would be estimated based on that y. Okay, because the parameter will be estimated on theta naught and y. This particular data simulation is not necessary because it's not estimation by simulation, but yeah, if we are to simulate, we need to follow this s1 is equal to s5 and s minus 1, right? We'll see some real life examples how Kalman filter is being used. Then multivariate Kalman filter LFAC multi. Let's read the question first. Consider the multivariate latent factor model. Now with n is equal to 3 variables, k is equal to 2 variables, compute prediction, observation and updating. Just like before, t is equal to, we have 5 observations. Now these are given to us, prediction, observation and updating, right? There is one very important thing, dimension. You need to remember about the dimension. You see lambda is a 2 variable thing, autoregressive parameter and lambda, they have the same number of columns. They are none of them are square, they are rectangular matrix lambda. But r on the other hand is the variance, sigma square v, sigma square and sigma square v. You have to remember r and q. R is a square matrix. On the other hand, this is very important to remember, sigma square is a square matrix and sigma square vq is a 2 by 2 identity matrix, which is the size of the autoregressive parameter. Autoregressive parameter is a squared matrix. A latent factor lambda or factor loading is not square at all. Okay, it is rectangular. That will be parameters actually that we'll estimate, because for n is equal to 3 variables you'll have this lambda, k is equal to 2 factors, so 3 by 2. Autoregressive parameter is a square matrix. In the same time, q, which is sigma square v, for us is a square matrix, which is a squared identity matrix. On the other hand, sigma square is a square matrix but not an identity matrix. So for y1, y2, 5 observations are given to us, at least 5 for each. Repeat with and change the observations. So this is the problem. Let's see. First start with function. So what are our inputs here? Y, phi, lambda, r, q. Quite a few inputs, right? Not b and y like univariate. We have y, phi, y, then autoregressive parameter phi, then lambda. These are all given to us. Lambda, r, q, all that is given to us, we are going to use them. So let's allocate the arrays. T rows on column will be size of y. So k is equal to, n is equal to 3, k is equal to 2. Because k is equal to 2, we have seen in our question, because k is equal to 2, q and phi both are 2, right? So k is equal to size of q rows one column, and log L will be 0 t1. So recursion initialize is s is equal to, we'll start with zeros. What is s0? S0 is equal to 0, which will have the dimension of k is equal to 2. So 0 k rows one column, then comes p. What was p0? P0 is equal to sigma square divided by 1 minus phi square, and that will be, p is also will be the size of k. So what do you have to do? Sigma square divided by 1 minus phi square. We know sigma square is q here in this question, and q is identity matrix. So 1 minus sigma square divided by 1 minus phi autoregressive parameter squared 1 minus phi square. So that is sigma square q, all elements of q, that is identity matrix multiplied to 1 minus phi square, right? So inverse of phi square, no, 1 minus 1 is identity k square, so we're taking the inverse. Identity k square is 1 because that will be must be in the same dimension as the autoregressive parameter minus phi square. Now phi square is phi into phi, that will be Kronecker product, okay? And so Kronecker phi into phi, Kronecker product will be phi squared. Beautiful. Something to remember, don't forget, Kronecker phi into phi will be phi squared. So all elements of phi will be multiplied with all the elements of phi. So what kind of matrix multiplication we have? Kronecker, Haldamam, and regular matrix multiplication. Now this will increase the dimension, as I believe, for the, so a 2 by 2 will be squared here. However, inverse of k is 2 by 2 will be squared. Okay, so this is squared and this is also squared, so they are the same, they are quite big, so they are the same, but they will be reshaped to have k rows and k columns. That's all, very simple. So it's reshaped. Okay, Q is as a vector, remember that Q is not a identity matrix, is we are using Q as a vector. This is something also to memorize in a multivariate model. Q is here not a matrix, all elements of Q are presented as vector, and k by k, that's all. So we reshape them and transpose the whole thing. So we have P105 P1 equals sigma square divided by 1 minus phi square. This simple equation is quite difficult to represent, but this equation we will memorize in this stage. Let's don't forget about this, something we started with, we just memorize. Then comes mu is equal to lambda s naught, that is as it is. Conditional mean, conditional variance, v10 is equal to lambda square p10 plus sigma square v plus sigma square, which is lambda square multiplied to, p1 plus sigma square is r, we know r, and what was our given value of r is there to with us, and then the prediction error is y 1 minus mu, and now y or 1 for all, row 1 for all columns transposed, so that we have a vector minus m, because m is a vector, yi y1, it automatically does that, rows minus, it automatically adjusts. Then we set the log likelihood function, half log twice pi minus half log determinant of vt minus half ut, just the one with the linear equation that we had, right? Fine. So that is with linear equation, that then we create the Kalman gain equation. We know what the Kalman gain equation is, lambda p10 divided by v10 inverse of vt. So lambda p10, lambda is here, if lambda was not in transpose form, we might need to put it in a transpose to change the dimension actually, that's all. If there, we need to check if their dimensions before multiplication, if the dimensions match. If the dimensions don't match, just do transpose. There is no specific thumb rule when to put transpose and when not, it's just to match the dimension, okay, inverse of vt, otherwise the multiplication will not work. Then s2 equal, then s11 equals s10 minus this is the regular equation that we all know, we just talked about. Then we create the observation loop just like univariate model, univariates prediction, univariates observation, univariates log likelihood, no change, univariates update, no change, right? And so the loop of our observation happens, it continues. So this function is ready and we are ready to call this function. So t is equal to 5, we take data from the text, we call the data that is given to us in transpose. Phi, lambda, r, q, these are given to us. Okay, as I said, we call for the Kalman filter. Here basically we created the simulation because y might need to be simulated here, so I don't think that is the reason. Anyway, y phi lambda rq, so we call the log likelihood function and we have y phi lambda variance. So just like the univariate model, what did we estimate in the univariate model? Lambda. We didn't estimate y. Here we are estimating y. We didn't estimate y. Now we have a new y estimated. That is a very important difference. Previously we didn't estimate y because in the univariate model, because we simulated y based on Kalman equation, latent factor model. This time our models are not latent factor model, so our system estimates a new y that is based on latent factor model. Then this is important, this is very important to remember. Then phi, lambda, rq, rest are the regular ones. Beautiful, and very important to remember, if you use used observation, then when you call the log likelihood function, that maximum likelihood function, you simply check in y2 so that it estimates y for you based on all the equation. If you simulate y, you don't need it. We generally don't use simulated, we generally use observed ones, so we need to pass in y. And so when we draw the function, we need to let them know, the system know, that I want y out of this. Okay, I want this y out. That will be my return. The function will return y for me, right? Exactly, the function will return this because I'm using them as input here. Okay, fine, but I want them to give this back, this function. This is the condition function. I want these out. So if x is equal to x square, kind of like that, right? So this is very important. I want these out from this function, even y, though I am giving some initial values. Beautiful, awesome. Let's move into the next one.